looks right. I thought there'd be data. Is anyone out there?
Okay, welcome back, everyone. We are talking about the Cremier-Rao lower bound. Actually, we're talking about dogs, but last time we were talking about the Cremier-Rao lower bound. So what we have is the setup here is we've got a one-dimensional theta, and we will kick that up to multiple dimensions, but right now I have theta, one-dimensional parameter, and then we want to estimate some function of theta, some tau of theta, which could just be tau of theta equals theta. And then we have an estimator, which is a statistic, so a random variable kind of look. And this is some kind of function of the data. And we have it that it is unbiased for tau of theta. Okay, so the punchline was under certain regularity conditions, which I will list. But as I said last time, regularity conditions are usually, things you need to make things nice. Is this continuous? Is this differentiable? That sort of thing. So under certain regularity conditions, then we have a lower bound for the variance of t. And t, let me just emphasize up here, is any unbiased estimator for tau. So no matter what unbiased estimator you can find, its variance can't get lower than this thing. So the variance of t is greater than or equal to tau prime of theta squared over the expected value of the derivative with respect to theta of the log of the joint PDF with the capital or random x's plugged in, and theta all squared, and then close that expectation. So this thing on the right is the CRLB. And in particular, the thing on the bottom has a name. It is, the thing on the bottom, I mean, if you've had any information theory, then this name would be more meaningful. But let me just say that the denominator, let me just say very colloquially, the denominator contains all the information from the data. And it is known as an information term, and specifically something called Fisher information. We're going to denote it by an I. I know it looks a lot like an indicator, but I don't think it will ever be confused with one. An IN of theta will be this denominator, and it is called the Fisher information. Hear all that crunching? Rufus is trying to make a nest out of my recycled papers. So yeah, this is called the Fisher information, and it contains all the information that comes out of the data. And it is the thing you have to compute primarily for this Cremier-Rao lower bound, because then I can switch up the problem kind of easily. If I have a sample from one distribution, like say a gamma distribution, and I want to estimate beta, I could compute this Cremier-Rao lower bound, and then if I wanted to talk about estimating the log of beta, that's a new function of beta, but the only thing that changes is in the numerator. So if you see this in a homework problem, and there's a part A, B, and C, it's likely that you don't have to do additional work for the second parts if what I'm doing, in fact, is asking you to find a Cremier-Rao lower bound for other things. Okay, so we're going to prove this, and as I said last time, I'm going to pick up the regularity conditions as we go. We're going to see what we need, but there's one that I do want to highlight before we go in. So this is one of the regularity conditions. And we need to be able to do the following. We need to be able to pass the derivative with respect to theta of the integral of f of the vector x and theta dx. And I guess I should say, like over here, when I'm integrating with respect to a vector, I mean to be just shorthanding an n-dimensional integral with a dx1 through dxn. So one of the conditions we need is we need to be able to pass that derivative past the integral. And this integral is going to be over the support of the distribution. So the thing that makes it integrate to 1. this one as well. And so we definitely can't do this if the parameter is involved in the support. For example, for the uniform zero theta distribution. And any of our distributions whose parameters are in the indicator, because we would be, if you had like a uniform zero theta, then you'd be integrating over that support and you'd be like, you can't just bypass that theta. So this is not going to hold for anything where the parameter's in the indicator. Okay, and the crux of the proof depends on the Cauchy-Schwarz inequality. And we'll prove this, which is actually most of the proof. Because once we have this, we really don't have to do much more to get the result. So you may have seen this before, and you may have seen it in terms of sums or integrals. I'm going to use integrals here, and we can generalize even more to expectations. So here's going to be my statement. You have two functions, f and g. These are not PDFs necessarily. And the Cauchy-Schwarz inequality says that if you integrate the product and then square that whole integral, this is less than or equal to the individual integrals with like squared arguments. So less than or equal to the integral of f squared of x dx. And then the same thing with the g in it. Okay, so this, as I was saying, also holds for sums, and it also holds for expectations. I'm not going to prove it in that case. It's very, very similar. But if I were to stick like a PDF in front of every dx, some PDF, then all of these are expectations of something. So does that make sense? It's confusing that I used an F in there that was not a PDF. Right, but if you take the expected value of some g of x, then you would put it in front of, so I've used up my F, right? So you put it in front of the PDF of x dx. And that PDF could like go all the way through this proof. So let's show it. Okay, so to prove it, I am going to consider the double integral of kind of a weird thing. I'm going to look at f of x times g of y minus f of y times g of x. And I'm going to square that whole thing and integrate with respect to y and with respect to x. Why am I doing that? Because two things. One, it gets me what I want. And another reason is because this thing is squared, I know that, let me move this proof. I know that this thing is greater than or equal to 0, which is going to be key in getting our inequality. So if you square this stuff out, you get the double integral of f squared x, g squared y, dy dx. So I'm squaring it out and running the integrals through, minus 2 integral f, oops, not squared, f of x, g of y, f of y, g of x, dy dx, plus, and that should be a double integral, the double integral of f squared y, g squared x dx. Okay, so these integrals are all over the entire space, like minus infinity to infinity. And so because of that, this integral, this first one is exactly the same as this one. Oops, I should put the dy dx. They're just variables, dummy variables of integration. So the first term and the third term are exactly the same. So I can write that as like 2 times just the first term. Right, so this is coming from the first term and the third term. And then the other guy, I've got a double integral with respect to first, in this case, y and then x. So if I kind of pull things out of the dy integral, I have an integral of the f of x, g of x, and then an integral f of y, g of y, dy dx. And then if I take this entire integral inside and pull it out of this integral, then we have the integral of f of x, g of x times the integral of f of y, g of y. And that's the same integral again. Wait a minute. Yeah, that's the same integral again. So this is going to be 2 times the double integral of f squared x, g squared y, dy dx. And after you manipulate things over there, you get minus 2 integral f, f of x, g of x, dx. And then you get another one with respect to y, but that's exactly the same thing. So up here you end up with minus 2 times the integral of f of x, g of x, dx, all squared. Okay, and this whole thing started with it was greater than or equal to 0. So from that, I can, move like this to the other side of the inequality, and that is what we wanted. That's exactly what we wanted to show. We can cancel the 2's. Sorry, yeah.
Okay, so for the last two, well, second to last step to the last step, you're just using the fact that there are no x or y's in the bounds of integration.
Yeah, yeah.
Cool. But
Yeah. Okay, so again, to grab this, move it to this side, multiply both sides by 1/2, and we're done. And we've got what we wanted, which was the integral f of x, g of x, dx squared is less than or equal to blah, 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 squared dx. Why do I continue to write this way where I don't fit on one line? G squared, I guess x or y doesn't matter, but that's what we wanted to show. And so again, I could have attached to each dx and dy, I could have attached a PDF. So I claim you can do something very similar and prove that you can get this kind of inequality out of expectations. And I'll leave that for you to play with, but if you want to see it at some point, come to an office hour or email me or demand it in class. So I want to get back to the proof of the Crimea lower bound. Okay, let's do it. Oop, rolling everywhere. Proof of the Crimea-Rao lower bound. So what's going on here is I have some distribution. So I have a joint PDF or a bunch of x's, which probably come from IID ones that are multiplied together. And we're trying to estimate some tau of theta, which very likely could be theta itself. And we have T, an unbiased estimator of the tau of theta. And so check this out. I'm going to start with the tau prime of theta squared, the thing that was in the numerator of the Crimea lower bound. You know what? I'm sorry. I want to back up. I want to show, I want to not square it. So if we can show that tau prime of theta is equal to the expected value of t minus tau of theta times the derivative with respect to theta of the log of f of the vector of x's and theta, then we would be done because we can apply the Cauchy-Schwarz inequality. So if we're looking at tau prime of theta, the numerator of the Crimea lower bound, and square it, that's the same thing as this expected value of these two guys, like all squared. And this is in place of like the integral of the f and the g. Like the expectation is like an integral and the f and the g. And so I could apply the Cauchy-Schwarz inequality right here and say that this is less than or equal to, by the Cauchy-Schwarz inequality, the expected value of t minus tau of theta squared on the inside of the expectation times the other one. And so you can see that we'd be done if we can show this because squared inside, because this is the variance of t. So if you look at all of these pieces, this and this and this, if you divide both sides by this, then you will have something that is below the variance of t. Then we'll have what we want. Provided that this thing is non-zero, which is going to be another regularity condition here. We don't want to be dividing by zero. We also don't want to be dividing by infinity. So let me start a list of our regularity conditions. I know I haven't proven the first statement yet. I just said that if we can prove this, then we're done by Cauchy-Schwarz. So let me know if you don't believe that, and then we'll go back and prove the top circled thing. Okay, so you know what, I'll save the regularity conditions till the end. So I want to prove this thing up here in this circle. So let's do it. I'm going to write out I'm going to start with the left side. So I have a tau prime of theta. This is the derivative with respect to theta of tau of theta. How clever am I? Tau of theta is the expected value of our estimator t, which is an unbiased estimator for tau. So this is the derivative with respect to theta of the expected value of t, because t is an unbiased estimator for tau. So our assumption is this expectation is equal to this. I'm going to write this as, so how would you do this expectation? The t here is a function of all of the x's, so like this vector. So this is the same thing as the derivative with respect to theta of the integral. Now this is representing an n-dimensional integral of the t with the little x's in. I'm not good at making that kind of lowercase script-ish t. And then because it's a function of all of the x's, you need to multiply by the joint PDF for all of the x's and integrate with respect to all of the x's, which is the same thing as if I had written n of these here and did a dx1 through dxn. So for the Chimera lower bound, recall this circle. In an effort for me to see something like a t minus tau, I'm gonna manipulate what we have here just a little bit. I'm going to write this as the derivative with respect to theta of the integral of t of x, and then f of x and theta dx, and then I'm going to subtract. This is going to look really goofy, but I'm motivated by looking at where I want to go. I'm going to subtract tau of theta, right? Because I'm trying to see that expected value of t minus tau kind of thing. And then I can't just do that, but I can if I multiply by the derivative with respect to theta of 1, because that's 0. So I can put that on. And I can get that 1 as an integral of the PDF. So I can write this as the derivative. I've determined that it takes me longer to cut and paste these things than to write it again. So this is a perfect opportunity for cut and paste. But this is going to be the derivative with respect to theta. Get rid of this stuff. Of the integral of f, the joint PDF, over, the heck, just a theta. Just a theta over all of the x's, because the joint PDF has to integrate to 1 when you do the n-dimensional integral. And all of these integrals are over the whole space, so minus infinity to infinity, or you can do that in indicators or use the actual space you have or something. Okay, so I am going to bring this stuff inside the integral. That involves the assumption that I stated at the beginning, and I will recap them at the end, that this derivative can go in and out of the integral. And I'm going to do the same thing over here. I'm going to pull this derivative in the integral under the assumption that that's doable. So if I did that, I would have, yeah, I'm just going to do that. I would have the integral d theta under the assumption that it's switchable like that, blah, 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 minus the integral of tau of theta d theta f of x and theta dx. And I'm trying to get this to look like the expected value of a t minus tau. And actually, okay, so let me move this derivative over here past that x, and let me put them together. This is the integral of t of x minus tau of theta, all multiplied by the derivative with respect to theta of f of x and theta dx. I want to turn this into an expectation, but in order to turn it into an expectation, I need to see just the, I just need to be integrating against the PDF, not against the derivative of the PDF, right? So in order to make this an expectation, I want just the joint PDF instead, so it looks like an expectation. So I'm going to do it. I'm going to take the thing that I have just under bracketed. I'm going to divide by the joint PDF and multiply by the joint PDF. And I've got t of x minus tau of theta. And then the derivative with respect to theta of f of x and theta over f of x and theta times f of x and theta. So the whole motivation for that was to kind of get an expected value here. And you might recognize this kind of derivative, a derivative of a function over the function itself. That is the derivative of the log of the function. So we're almost done. I think second to last line or last line. This is the integral of t of x minus tau of theta times the derivative with respect to theta of the log of f of x and theta times the f of x and theta dx. Get some space there. And in the coming few lectures, we're going to use that trick a lot, where we take a derivative and we divide by a PDF and multiply by a PDF so that we can take an expectation and we'll turn it into a log. Okay, so I now have, I close this. I now have like a function of little x in front of the PDF for the little x. So this is the definition of the expected value of t of capital X minus tau of theta times the derivative with respect to theta of the log of f of capital X and theta. And that's what I wanted, because this t of capital X is the capital T. And sorry if you're copying, I'm coming right back. But we wanted to show this thing. And that's what we got to. So we did it. Yay us. Now I want to write down the conditions that we needed. Like, in a few places I said, oh, assume you can do this, or assume you can divide by this, but what if it's 0? Stuff like that. So here they are, the regularity conditions, the so-called regularity conditions for the Chimera lower bound. I am not going to try to trick you. You're not going to have to, in this class, check that they hold. The only one that's really important is being able to bring the derivative with respect to theta past an integral, and you can't do that if the integral bounds involves theta. So just remember that you can never use the Chimera lower bound when the parameter's in the indicator. The first one, I've got 3, is that we can move this derivative inside and outside of this sort of integral. And if we have another function of x in front, that's not going to change this property. So if this PDF, let's just say it's one-dimensional, so n is 1, then if you had, say, a uniform, say n was 1, if you had a uniform here, like x and theta, and it was 1 over theta on 0 to theta, don't write this down, then yeah, you would have an indicator inside the integral, and you could imagine writing this as generally minus infinity to infinity, but it is equivalent to the integral from 0 to infinity, and you can't move the derivative past that. So I know there might be some temptation to say it's minus infinity to infinity, move the derivative past that, and then you've got an indicator inside your derivative. But so this is the condition that says the parameter can't be in the indicator. The next thing we used is we needed that derivative of that log to exist. So we need the derivative with respect to theta of the log of the joint PDF. We need it to exist. Because I suddenly did this trick where I rewrote something in terms of this. And the final thing we needed is for the very last step. We said we'd be done if we can show this, and that is because if we square this side, that means we square all of this. And by Cauchy-Schwarz, that's less than or equal to this with the square inside the expectation times this with the square inside the expectation. And so the three things that are circled in yellow, I get the Cauchy-Schwarz inequality, I get the variance of t greater than something by dividing by this. So we can't divide by that if it's 0, and we can't make sense of that division if it's infinite. So the final condition is that we have this expectation greater than 0 and less than infinity. And again, I won't try to trick you, so you don't have to know these conditions or check that they hold. If I'm asking you for Chimera lower bound, it's gonna make sense. I'm gonna do one quick example just to say we did it, but I've got a few computational simplifications for you that I think you're gonna wanna use. So all of the work in a Chimera lower bound goes into computing that Fisher information. And so let's do our simplest random variable, nice and discrete, 0 and 1. You guessed it, the Bernoulli. So as my first example, I've got a random sample or IID x1 through xn from the Bernoulli distribution with parameter p. And so I'm going to have two parts to this. I'm just going to list them right up front because we're pretty much going to do them together. I want to find the Crimea-Rao lower bound for p. Now, the first thing I want to say is that line doesn't make sense because it's not bounding p. It's bounding the variance of all unbiased estimators of p. So if you wanted to be technically correct here, you would say for the variance of all unbiased estimators of p. All possible unbiased estimators of p. But that's a lot to say. So we usually just say the Crimea lower bound for theta or for theta squared or whatever. And the second part is going to be to find the Crimea-Rao lower bound for a function tau of p that's going to be p times 1 minus p. So it doesn't matter what this is, it's just an example, but this happens to be the variance of the distribution, which we could estimate with the sample variance. And if we have the n minus 1, it will be unbiased. And therefore, the variance of that sample variance is going to be above, guaranteed to be above the Crimea lower bound. And again, as I said last time, if you have an unbiased estimator whose variance equals or achieves the Crimea lower bound, you necessarily have the UMVU. But there's way more to the UMVU than that because the UMVU does not have to achieve the Crimea lower bound. It may be just way too low, not a sharp bound. Okay, so let's do this here. In the first part A, I've got tau of p equals p. And all of the work in this problem is to find that Fisher information. So I only need to do that once, and then I can answer A and B really quickly. So let's find we need the PDF. The PDF in this case is p to the x, 1 minus p to the 1 minus x. That's how you get the p and 1 minus p for 1 and 0. And yes, it has an indicator, but you do not, as we talked about last time, take the log of the indicator, take the derivative of the indicator. You do not involve it in the computations. And just to be clear again if I had like a piecewise defined function and it was defined on certain regions. You know, if you were to take the integral, you would take it in pieces, but you would not be taking the derivative, derivative, but you would not be taking the derivative of the supports. So I would just ignore the indicator. Is A, it's not involved in your computation, and B, this would not work in any case where the indicator is especially important. When the parameters in the indicator, the Crimera lower bound is not necessarily a lower bound on the variance of all unbiased estimators. Okay, so I'm going to ignore the indicators, and next I'm going to write the joint PDF. And so this is f of a vector. And because these guys are IID, I'm going to just put xi's in for the x's and multiply them together. So this is p to the sum of the xi, 1 minus p, n minus the sum of the xi. And then we need to build up the Fisher information. So the next thing is the log of the joint PDF. And this is the sum of the x's times the log of p plus n minus the sum of the x's times the log of 1 minus p. Okay, and then we need to take its derivative, and then we need to square it, and then we need to put in the capital X's and take the expected value. So let's get the derivative with respect to theta. In this case, that is p log of f of x as a vector, and p. So this is the derivative of log of p is 1 over p. So this is the sum of the x's over p. And the derivative of the log of 1 minus p is negative 1 over 1 minus p. So this is minus n minus the sum of the x's over 1 minus p. This looks similar to what we've done finding the MLEs, but unlike finding the MLEs, we're not setting this equal to 0 and solving for something, because when we, well, we're not, but when we did that, we were able to multiply through by anything we wanted to make it simpler, you know, and cancel stuff, but we can't cancel anything here. We're going to have to put capital X's in, square it, and take the expected value. So I think the first thing I want to do here is try to combine this into one term. So this is going to be the sum of the x's times 1 minus p minus n minus the sum of the x's times p over p, 1 minus p, and minus p plus p. So this term is going to end up canceling with this term, and I think that's it. Yeah, so this is going to be the sum of the x's minus np over p, 1 minus p. I don't ever want to do it this way again. I'm hoping to get to the computational simplifications pretty shortly here, but we're ready to go. The n-dimensional Fisher information, so it has the subscript n to talk about the number of things in the sample that went into it, is the expected value of this derivative, of this log, of the f with the capital X's, all squared. And this is going to be the expected value of the sum of the capital X's minus np over p, 1 minus p, all squared. And I'm going to get that the denominator out of there. That's non-random, so I can pull it out to get 1 over p squared, 1 minus p squared. The expected value of the sum of the x's minus np, all squared. Couple ways you can think about this. One, you can say, oh, I know the distribution of this. Like if I let y be the sum of the x's and I started with n different Bernoullis, that's going to have a binomial distribution with parameters n and p. Another thing I could do is I can put like 1 over n here and 1 over n here and multiply by an n out front and turn it into an x bar sort of thing. So however you want to do it, the expected value of this binomial is going to be n times p, and the variance of the binomial is np 1 minus p. And so what I have written here is 1 minus p squared. This is the variance of y, where y is that binomial. And so you can just look that up in the table. You go to the the table, look at the binomial NP, and you get blah, 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 NP 1 minus P. And so I get N over P 1 minus P. That is the Fisher information. I still have to put it together in the Crimera lower bound, but is there anything I can clear up there? And I wouldn't worry if that seemed hard because I've got computational simplifications that I think you're going to love. So for part A, we wanted the Crimera lower bound for the variance of all unbiased estimators of P. And so the Crimera lower bound, like you might put a sub P or something if you're comparing a few things, is going to be tau prime of P squared over the n-dimensional Fisher information. When I take the derivative of this, I get 1. I square it over n over P, 1 minus P, and I get P 1 minus P over n. That numerator is the variance for the Bernoulli distribution, which is what we started with. Can you think of an estimator for the mean of the Bernoulli distribution, which is P, that has this as its variance?
Sample mean?
Yeah, exactly, the sample mean, right? So the expected value of the sample mean for these Bernoullis is P, and the variance is the variance for one of them, which I said was P times 1 minus P. So this value is coming from the Bernoulli chart. So there's an unbiased estimator whose variance is as small as it can possibly be. We'll actually see later that that is the UMVU for P for this problem. Okay, so for part B, we had that we were trying to find a Crimera lower bound for the variance of all estimators of P times 1 minus P. And the point I wanted to make is that everything stays the same except the numerator. So the Crimera lower bound for tau of P is going to be the derivative of this with respect to P. So it's going to be 1 minus 2P. And that gets squared and put over the Fisher information. And so we end up with P 1 minus P 1 minus 2P squared over n. And so if you were looking for estimators of this and you came up with some that were unbiased, like we did at the beginning of class, we were just sort of guessing, and you computed their variances, you could compare it to this Crimera lower bound and say, do I think I have a low one? But that's not the greatest idea because this lower bound may just be very low. Again, may not be a sharp bound. But if you do get close to it, then you know you're kind of doing okay. I only have a few minutes left, but I want to start off with, so I've got 3, we won't get to all of these, computational simplifications that I think you will really want to take advantage of. Wouldn't it be cool if we could do that expected value of that derivative of the log of the joint PDF squared with just like n equals 1? Then I could have worked with the Bernoulli instead of the binomial. And in other cases where I don't know the distribution of sums of things, like it's so much easier if you can just work with one of them. And that's what we're leading up to. So I call this computational simplification 0 because it's not something you're really going to use, but you use it to prove the others and actually to prove other things. And this is that the expected value of the derivative with respect to theta of the log of f of x and theta without the squared is 0. This thing inside, I'm not going to use the terminology very much, but if you see it somewhere else, this is known as the score function. Okay, so I've got a minute to prove it, and that's all I need. The expected value of the derivative with respect to theta of the log of f of the vector x and theta. This is just a function of the vector x, so I need to put it in front of the joint PDF for the vector, or the PDF for the vector, and integrate. So this is the integral d theta log f of little x and theta, and that all gets multiplied by f of the vector x and theta, and I integrate with respect to x, because this is just a function of x, the vector. Okay, this derivative is the derivative of the f over the f itself. So then I'm going to get cancellation. I'm a little rushing. So This is I'll probably recap this one. This is the derivative of the PDF, all integrated, and we assume that we can pull this out. And that PDF integrates to 1. So this is the derivative with respect to theta of 1, which is 0. I'm out of time. I will see you next time on mathematical statistics.